The physical structure provides a home for all the components of the satellite. The basic shape of the structure depends on the method of stabilization employed to keep the satellite stable and pointing in the desired direction, usually to keep the antennas properly oriented towards Earth. Actually, two kind of stabilizations are used. In older satellites, they have used spin stabilized system, and nowadays instead of spin stabilization, they use 3-axis or body stabilized kind of technology. In the spin stabilized satellite, generally they are cylindrical in shape, and for 3-axis or body stabilized satellite, their shapes are completely different. In spin stabilized satellite, uh, the solar cells are placed, uh, generally they were placed on the body of the satellite, like that means on the cylinder. But for 3-axis stabilized, we have separate housing uh, for this particular kind of satellite. So we can have longer um, or larger uh, solar panel, but here the size of the solar panel or area of the solar panel is limited. Okay, so these are two kind of stabilized stabilization technology used for satellite communication system. The main objective that we have already discussed, that to point the antenna, communication antenna, in a particular direction. Okay, sometimes it may change. If it tries to change, then some necessary action should be taken to mitigate that particular change. So let us first discuss spin stabilization. A spin stabilized satellite is usually cylindrical in shape, that we have already said. For geo satellites, the spin axis is maintained parallel to the spin axis of the Earth, with the spin rates in the range of 30 to 100 revolutions per minute. Impulse type thrusters or jets are used to maintain the spin rate and correct any wobbling or nuttation of the satellite spin axis. There may be some change in the spin axis, there may be some change in orientation or change in speed, angular speed, something like that. Now, entire spacecraft rotates for the spin stabilized satellite that employs omnidirectional antennas. When directional antennas are used, which is the usual case, the antenna subsystem must be despun. Now, what is the meaning of this despun? Okay, see, whenever a body rotates about itself, the corresponding antenna will rotate along with the body, right? So if I want to make this uh, antenna direction constant, we have to make sure that with the rotation of the original body, the antenna should be rotated in other direction. Okay, so if the the body is rotating in counterclockwise direction, that particular platform on which the antenna is there, that should be rotated in the clockwise direction with same angular velocity. That is what we call the despun. Okay, so under that condition, the antenna will maintain its orientation in a particular direction. In 3-axis stabilization system, the stabilization is maintained with stabilizing elements. So there are certain stabilizing elements present in those satellites for each of the 3 axes, and those 3 axes are called roll, pitch, and yaw. So if this is the condition, like this is the Earth, this one is the satellite, so this direction is the yaw direction, this direction is the roll direction, and this one will be the pitch direction. So this is actually the conventional way um, of calling three rotational axes, just like XYZ in translational uh, change. We have roll, pitch, and yaw in rotational condition. The entire body of the spacecraft remains fixed in space relative to the Earth, right? Control jets or reaction wheels, sometimes like flywheels type of thing, are used either separately or in combination to provide correction and control for each of the three axes. That means for each axis, like in this direction, in this direction, in this direction, we have some kind of flywheel type of thing. So whenever the body or the antenna will try to change its direction, so corresponding to that change, it will be measured in which direction it is trying to change, and based on that, the corresponding flywheel will start to rotate. Okay, in such a fashion that it will generate some angular momentum, and that angular momentum will return the satellite antenna in its original direction. So that's the technique. After stabilization, we are now going to discuss the orbit control. Suppose the situation is, this is Earth, this is the equatorial plane of the Earth, right? And this is the original position of the spacecraft or satellite. But due to some reason, maybe due to the force uh, acting on the satellite due to sun or moon, the inclination angle of the satellite has been changed. That means now the satellite is rotating in this inclined orbit like this one. Okay, so from any point on the Earth, the satellite, instead of uh, observing the satellite in that particular direction, the satellite will now be observed in this particular direction. That means the satellite will be moved in a north-south direction. Now, if the it was if this change is detected, change in position of the satellite or inclination angle change is detected, what we should do? Actually, there are number of jets or engines or thrusters present on the satellite. Depending on the amount of or shift in inclination or shift in position, etc., different engines are fired, sometimes automatically, sometimes some command must be given from the ground station, and based on that, engines are fired for specific period of time, and those engines will correct the change in position, right? That means once the engine is fired, the satellite will move to its original position, and it will try to remain in that particular position for another period of time. The point is, for each correction, we need to fire rocket or jets or engines, right? And for each time, it will consume some fuel. Now, before launching of the satellite, we must store, or we must rather send sufficient amount of such fuel for this control, for to control the orbit or to control the inclination angle. What will happen if the fuel is exhausted? If the fuel is exhausted, then the thrusters will not work, right? That means the satellite will not be in its own position, it will change its position, and we are not able to move it back to its original position because all the fuels are now exhausted, right? And that's the end of the satellite lifetime. Get it? That means we have to provide sufficient amount of fuel in the satellite itself. Otherwise, the satellite will not be controlled properly, right? So before launching the satellite, we must have some idea how much fuel is required. Mind it, we cannot we cannot have huge amount of fuel because of the cost of launching will be increased. If we want to provide huge amount of fuel, the cost of launching of that particular satellite will be extremely high. So we have to set a particular lifetime for just for the satellite. Like we have assumed that lifetime of the satellite is say 10 years or 12 years, and we must have some idea that how much correction is needed within that period of time, right? And corresponding amount of fuel, that means the within 10 to 12 years, how much fuel is required to position the satellite in its own location. And based on that, we have to provide that amount of fuel. Okay, now it may happen that within that span of uh, time, the fuel is not exhausted, right? So that will actually extend the lifetime of the satellite. But if some other, on the contrary, if it happens that we have to control the satellite uh, much more times than it was originally designed, that means uh, the total fuel is exhausted within say 8 years, that means it will reduce the lifetime of that particular satellite. So lot of things are there. um, Sometimes some unwanted situation arises. Because of that, we have to use the fuel, um, unnecessary use of we maybe we have used the fuel. So under those conditions, the satellite lifetime will be reduced. Okay, so uh, the issue is how we can control the orbit in its proper position with minimum use of fuel. So that is the objective of this orbit control system. Okay.